then you don't have to worry about getting hired somewhere. No. So I can buy lunch at the corporation.
Okay. Sorry to be late. How's everybody doing?
Good.
Good? Thumbs up, right on. Any questions as we get started? You saw the announcement about next week. No class. Take the extra time to work on your final projects. I'll be out of town, so would be a trick to try to scramble to get some other lectures put together for, say, like TAs or something like that. So apologize if that wasn't your plan, but that is the plan now, and yeah, just use the extra time. What else? Still need to hear from some of you on the comments I made on project plans. I'm sure nobody here in this physically in the room right now, but really hope that I'll get those soon. Okay, well, let's get going then. We're already at 10 minutes behind. So this is part 2 of reinforcement learning. So last time we framed how how we think about reinforcement learning, how we go about like expressing what it is and like what problem we're trying to solve. Basically, it's this idea of finding policies that maximize the cumulative discounted reward. In this situation where we've got an environment, an agent, we're talking about a single policy for a single agent. Of course, this can be expanded to have multiple agents, each with their own policies, but yeah, so this is like the key, the key value that we're trying to optimize. And then we kind of built up some theory around this to do what's called Q learning, and then when we use neural networks, deep Q learning. So we defined a value function, which gives you a way of assigning a value to a state. We defined a Q value function, which gives you a way of assigning a value to something like the goodness to both a state and an action. Again, both of these given the policy. And then we talked about the optimal Q value function being the one associated with the with the policy that maximizes the value in that state in that state action pair. And then we said, okay, great. This is all just a bunch of like gobbledygook math. How does this help us do anything? Then we introduced some more gobbledygook math, the Bellman equation. But importantly, it's a recurrence relationship for the optimal Q value function. And so we said, okay, great. What do we do with that? Well, from previous experience with recurrence relationships like this, we know that there are methods for solving it. In particular, we can iterate this, updating the function by plugging its values in to the right-hand side here. And then we said, cool, why don't we, instead of trying to like actually figure this thing out for all states and actions, enumerating all those and trying to work through it all, why don't we do the thing that we learned to do in this class? We estimate the Q function with a neural network, and then we say, okay, great. If we do that, that's fine, but we need an objective to optimize, something that we're going to perform, gradient descent on. And so we came up with this loss function right here, which is matching the Q value function for the current set of parameters with this like right-hand side with the previous parameters. This gives us this like idea of like iterating right from one Q value function to the next. And we update our parameters, getting us the next set of parameters using this by doing gradient descent. We compute the partial derivatives of the loss with respect to our parameters, and then update the parameters. There's our gradient. It's kind of messy, but it gives us a way to actually learn the Q function. And then if we have an optimal Q function, we essentially have access to the optimal policy by looking at the Q value function, taking the state that we're currently in, and then looking at all the possible Q values for that state across all the actions, and then picking the one that gives us the maximum, picking the action that gives us the maximum Q value. And then, that's implicitly, that's our optimal policy. So now we have an optimal policy, and we have a great agent that's following an optimal policy. Questions on that? That's everything from last time. Yeah.
This might be a hard question to answer, but I'm trying to maybe wrap my head around what the neural network is modeling as.
Oh yeah.
And I'm wondering if you have any really simple examples.
Yeah, like an Atari example? Yeah, let's do it. Okay, so case study, playing Atari games. What would this look like? What would a Q value function look like here, and how would it, what would learning be? Remember, what's happening here? The reason why a lot of this research kind of started early on, and still is used to establish baselines with Atari games, is because the state is explicit, even if it's complex, it's explicit. It's just like these pixel values from the screen. You have scores usually associated with it, but importantly, the action space is really controlled, right? You have a joystick, and at every time step, that joystick, is giving it it's the input for what the action should be, right? Whatever left, right, up, down, button push, it can get a little more complicated than that, but those are the actions you can take that correspond to something in the game, the changing of the state of the game. And so it's pretty straightforward. So what does that look like? So let's say we're playing Breakout, right? And remember, Breakout is this thing where we can move this paddle left or right, or not do anything at all, just stay in the same spot. And there's one other action. What is it? Because there's 4 actions in this example. I can't think of what it is right now. I don't know. So maybe there's only 3 actions. But anyways, there's various the actions you can take. There's very few of them. Okay. So what that means is that we have a neural network that's approximating, or it's estimating our Q value function, and it needs to be its output needs to be something that will give a value for a state and an action pair. Okay? So we need to decide on what the state is. So in the particular example we're going to look at, the state will be the last 4 frames of the game. So it could be the current frame of the game. In this example, the last 4 frames of the game, and that's our state. So we're going to have the numbers you're seeing here, 84 by 84. We can think of this as being downsampled, cropped into an 84 by 84 array of pixels. There's not a ×3 here. We actually go to grayscale. The colors don't help; they don't matter in this particular game. So, even though there are colors here, it doesn't really matter. So, those are then converted to grayscale as well. So that's 84 by 84 by 1 for one of these frames, and then there's 4 frames. So this state is represented by an 84 by 84 by 4 tensor. Okay. So that's the input. So now we need a network that's going to, so that's our states. Now we have to do something about the actions, right? So the way that we go about this is this is input into a convolutional network. So here's a very simple example. Couple of layers with, in this case, an 8x8 conv layer, strike 4, 16 filters. That feeds into a 4x4 conv layer, 32 filters, strike 2, okay? And then that's going to get us to that'll give us a feature map of a particular size. We're going to have a fully connected layer, and then another one that's going to be basically the scores, the Q values, across each of our actions. And so this thing's now going to have, this is why I was saying earlier, I can't think of what the fourth action is actually. Left, right, don't do anything. Anybody else can think of it? Maybe it should be FC3. Some other cool action. Press the button to pause or something like that. I don't know.
Maybe the ball hits the paddle, you have to press the button again to release it.
I don't think it's how it works,
That's
but
not how it works.
yeah, there's one more action in there in this example. I don't remember what it is. Doesn't matter. Whether that was 3 or 4, what that's going to give is those are the things that we're going to try to train to be the optimal Q values. Okay. So now what that means is that we inputted the state here, and then up here is where we have the state and the action. So it's going to be for that one state, all 4 or 3 actions. And so that's how this particular setup is going to represent Q of S and A. Okay, so I'm going to go through more of this, but just want to stop and see if that started to make sense.
Yes, it started to make sense. I guess the thing that is still confusing to me is how do you score the actions? We go to the
Right. Okay, good. How do we score the actions? Remember, this is what we're doing. This is our objective right here. So we don't actually have the scores, right? We actually don't know what the values are. We aren't supervised by the actual values for that state in action. What we know is that if we get something that satisfies this Bellman equation, then it's going to be our optimal. It's going to be the optimal Q value function. Whatever the actual values end up being, that's going to be optimal. So we have this kind of interesting, loss function and way of updating the parameters that depends on the previous parameters. That is performing this iteration right here. That is known to, if this right here, if this right hand side, this functional, meaning it's a function of a function, if this functional behaves in certain ways, then there's a theorem here, the contraction mapping theorem, that says that this thing's going to converge to something, which is going to be a value that satisfies the left and right hand side here. So we don't know what the Q values are. We just know if we keep doing this and get ourselves close to the quality there, then we're going to be close to the optimal Q value function. Whatever those values are, that's what they are. Make sense? So whatever comes out, whatever comes out here is going to, be, the Q values here, and then from our previous iteration, the previous values of the parameters, that's going to give us this Y here, and whatever they all are, we're just trying to minimize it. So it's different from what we've done in the past. It's not. I mean, there's a kind of supervision happening, which always happens when we're training neural networks, because we have to have this loss function. It has to be explicit, but you have this kind of what's often called a student-teacher kind of relationship here, which is where we have some representation of our function, which is the teacher that's trying to train the student, and that's what's happening here. We have the teacher happens to be our neural network from the previous iteration. the student is the one that is currently learning. So it's a little bit weird, but this is the motivation for it, is like we're trying to do this iteration so that, you know, every time we update the parameters, you know, in this way, if we do that long enough, we're going to get closer and closer to this being an equality. And when that's an equality, we have an optimal key value function. And when we have an optimal key value function, then we have an optimal policy.
Is each I a key value in this case?
Yeah. Mm-hmm. Yeah. Yep. Yeah.
So is it at all right to think about it as though you're kind of like pretending to be regressive? Because like instead of actually using regression, like go back to the beginning.
Yeah. I mean, you're not pretending. You're not pretending, but I know why you're saying that. This is a regression problem, right? This is like, you know, mean squared error in some sense. But like, what's the thing that you're trying, like, and we suggestively wrote yi here, like this is the label that we're trying to match. But this label is unusual. It's not the label that, like, you know, like the bounding box corner or whatever, you know, like from you know, object localization or whatever else you're doing. It's this funky thing that we create from the previous iteration. Yeah. Thanks for the good questions to get us to hopefully at least one student here understanding. I hope, you know, the rest of you, if you understand it, great. If you don't, please ask questions, or forever just sit in ignorance. I don't know. Okay, makes sense? Makes sense? Okay, great. So in this example, that's how we get these Q value functions, or the Q values. Our state, you know, our conv layers, folded connected layers, and yeah. This would be, you know, FCN, where N is the number of actions that can be taken in that state. So it says 4 here. I can only think of 3 for breakout. If you know, other games might be, you know, before might be left, right, up, down, you know, something like that. Okay. Yeah. Number of actions can be between 4 or maybe 3 and 18, depending on the entire game. I suppose there are other actions that are like up and down in there that don't do anything. Okay, so single forward pass to compute the Q values for all actions from the current state. This is actually one of the benefits of Q value learning is the way that we set these up and we learn them, right? Is that our network, no matter how many actions, so that like the training might actually be really laborious and might be really costly, but once we have a trained Q value function, in setting it up in this way, we can get the Q values for all the actions in one forward pass, right, at inference time. This is often the case with neural network. What's happening is that the training and such is the thing that's mostly is very costly, and oftentimes that translates into, you know, very fast and efficient inference time. So like we amortize all the costs of these things, you know, typically in training. All right. So I'm going to move on to like some of the like how you actually do the training in this case to make it more efficient. But I don't want to leave this slide until like just kind of if this example helped you understand what's going on here and how we're formulating the network that estimates a Q value function, and then like how we're optimizing it. Any more questions? All right, so training it. So how would you go about training these things? Well, I guess you just have like a bunch of games being played, right? I mean, how else would you do it? And that's fine, except for the fact that remember in all of there's this underlying assumption when you're training in machine learning, and it's often violated, but there really is this assumption that that your training samples and your test samples are sampled IID, so independent and from identical distributions, right? And really not the case when you look at like a game, right? If you think about like, you know, frame after frame, they're very correlated with what's happened before, especially, you know, nearby frames in time, right? Like if I'm, you know, wherever I am right here at time t plus 1 is going to look very similar, except that maybe the paddle's moved right or left, and the, you know, the ball has, you know, moved very close to where it was before. So like that is a very correlated outcome, and that's very problematic because it does violate the IID assumption. And what matters about the IID assumption? Well, the two things that matter. One is the bigger problem, which is like if your test set isn't the sampled IID in the same way as your training set, then you're not getting a good estimate of like the generalization error of your model. That's a problem. But the other one is that you can have very inefficient learning, right? If you're training on very correlated samples, then you're getting very biased like gradient estimates, you know, like when you're updating your parameters, because they're all like in some way similar to each other. And remember when we're doing stochastic gradient descent, you think back all the way to the beginning of the course, you know, the idea was that we want to estimate the gradient for the full data set from just a small mini batch. And that becomes really a bad estimate when our mini batch is biased in some way, and this will be if we just kind of like run linearly like through like the frames of the game or something like that. So we need to like prevent that. And one really simple way that's used all the time in training these kinds of networks is something called experience replay. So what's experience replay? Well, it's that we're continually updating just like a memory, you know, like just like a lookup table, what we call a replay memory, the table, of just all these transitions, right? So we have a state, we take an action, we get a reward, and then we update to the next state. Just as you go through the games. And then when we're training, we randomly sample from that table of, that replay memory table of those transitions. So that instead of getting consecutive samples, we get, you know, random samples from like, from even within the same game or across mini games or whatever. Many episodes as they're often called. Okay, so it's really a simple, you know, idea and technique. You just like you play the game, you fill up this, instead of just like playing the game and just forgetting about the states that you were in and the rewards that you got from that, you actually save them, and then when you are training, you just randomly sample from those. So pretty simple, really effective. Okay. Whoops, what did I write there? Each transition can also contribute to multiple weight updates. Yes, right. So another thing here, if you think about it, so if we're doing this random sampling from a table, we don't just like see the transition once and then, you know, lose it. It'll be there when it could be part of, you know, various different mini batches, and that is more efficient. So this is, you know, like pseudocode or, you know, simple algorithm for what this looks like. How do we do deep Q learning with experience replay? So we initialize, you know, when we start this off, obviously we initialize the memory, you know, wipe it out. We initialize our network, random parameters or random weights. And then we do have our, like, you know, we have our data, which is like the full games being played. And we start working our way through those. You know, we get set up, we have our initial state, however the game starts. And then, you know, however we're representing the, you know, that state. Remember, like in the example that we just gave for breakout, how we actually do some resizing, some cropping, some converting to grayscale, that kind of thing. But then importantly, what do we do as we move through the game? So we start randomly selecting actions to take, or it's right here, sorry. There's kind of two ways to go through this. We randomly select actions to take, or we select the action that maximizes, you know, the current Q value function. We take that action, we observe the reward to get the next state, we store that in memory, and then now all that was to like start to fill up the replay buffer, And now we sample from that and perform a gradient descent step. Oops, sorry. And the way that we set the rewards are, you know, like the label that we're trying to match with the current Q value function is either the reward if we've hit like the end of the game, or, you know, this value right here, which is, you know, the inside of that expectation on the right-hand side of the development equation. And then, you know, now we have our yi, we have the current Q value function for each of the actions. There's our loss function, we perform gradient descent, and we iterate. So, a lot of complicated kind of background to get to here, but a pretty simple training procedure nonetheless, and it's really, really effective. Questions on that? So this is like standard, you know, reinforcement learning with neural networks, deep Q learning, and of course the Q comes from the fact that the thing that we're learning, the thing that what the neural network is in this problem setup for reinforcement learning is the Q value function. Any other questions? Okay. So, well, is that the only way we could do this? No. We could do this in different ways. So we're gonna talk about two. One is policy gradient. So basically this is, now we're gonna change what the neural network is estimating. So in deep Q learning it was the Q value function. Now we're actually going to have the policy itself be a neural network. And then the actor-critic model is essentially combining the two. We're going to have both deep Q learning and policy gradient learning. And one will be the actor, that's the policy. One will be the critic, that's the Q value function. And reinforce here is the name of the algorithm that we use to update the parameters of our policy. That's why it's sitting there like that. And this is a very, very common algorithm to use in reinforcement learning with neural networks. All right. So, what are the problems with Q learning? Any thoughts? Are there any problems? Seems good. Works. Works great for DeepMind. Why should we care? Any thoughts? Yeah.
Lots of data.
Say it again.
Lots of data.
We need lots of data. Okay. Yeah, we do need lots of data. That's probably true for you know, many of the ways that you train here. You do need lots of data, but there's something kind of related to that is like, I guess, the thing that I'm looking for here, and that is our Q functions can be pretty complicated, and this has to do with, you know, how complex the state can be, but in particular also like how complex the action space can be. Remember, what we're learning is like this is a function over the state and action pairs, right? So if either one of those is complex, already we have a complex, you know, space on which we're learning the Q value function. But if they're both complex, you know, this is far worse. So it can be meaning like this can be like a very, very, very high dimensional space, this like state cross action space. So an example here is, think about, you know, a robot grasping an object, right? Like the state space is complicated. If you know, if you just think about just the hand, there can be, you know, if it's like a truly humanoid hand, we just think about all of the joints we have here and keeping track of all of the, you know, degrees of freedom for each one of those joints. And then also like its position, you know, within three-dimensional space, its relationship to the object it's trying to grasp, so on and so forth, right? This already is very complicated, never mind the rest of the robot, right? So this can pose a huge challenge, right? Just like the space is way too big, we probably don't have enough data, you know, in those cases to like really, you know, kind of explore the full range of different, like of all the states, you know, that this could be in, that the robot in this case could be in. So, kind of getting back to your point about not, you know, this requiring a lot of data. How much data it needs, really depends a lot on how complex the state and action spaces are. So, if we think about it though, like the policy is much simpler, just reward for, you know, just closing the hand, whatever closing the hand is, right? It's a kind of this higher level way of thinking about the action that's happening. So, there might be an advantage if we can learn the policy directly. All right, so how do we go about this? So what we're going to do, like I said, is that we're going to have our policy now be a neural network, right? So you see our favorite theta as a subscript there on pi, the policy. That just means that this is now, you know, a neural network parameterized by all the weights theta. Okay. And remember what the policy is, right? The policy is a way of assigning basically like, you know, probabilities to the actions that you would take given the state that you're in, right? That's what a policy is. So when we say that, this is a distribution. This is a family of distributions that are being parameterized by theta. All right. So now, you know, whatever the policy is, you know, it depends on these weights theta. We want to derive its value, right? And so that is this objective that we've, you know, the cumulative discounted reward that we want to, that's like the core object that we want to optimize. So we're giving it now just a name J because we're going to keep referring to it. We're going to take gradients of it. So that's what J is. J is this objective, the value here, the cumulative discounted reward. For, it's a function of the weight. So for, you know, for theta, for the particular policy, that's represented by those weights theta. All right. So we need, so anyways, that's the value that we're going to be taking gradients of because we're going to want to maximize this thing, right? The optimal policy is the one that with weights that maximize that sum. So how do we go about this? We are going to perform some kind of, you know, gradient operation. We want to maximize this, so we want to perform gradient ascent instead of descent here. But we know how to do that. We've worked with that already. So great, gradient ascent on this function here. Well, how do we do that? Well, it's kind of a tricky, you know. We had to do some crazy things before, come up with these value functions, Q value functions, find, you know, use a you know, somewhat difficult to understand recurrence relationship in the Bellman equation to be able to kind of even work with that. So how will things proceed here? What kind of like you know, what kind of trickery are we going to have to do to get to this? And there's a bit of trickery. That's what we're going to do next. So this is getting into like the reinforced algorithm. What does it look like? All right. So the way that we think about this, the way it's helpful to think about this and getting into the theory here is to rewrite this function j, again the expected cumulative discounted reward, as an expectation over the full trajectory, and the trajectory here being the triples state action reward, state action reward, state action reward, just as a full sequence. Okay, so like think of it as the trajectory that the agent is sort of like, you know, mapping out or, you know, walking in this interesting space of state cross action cross reward. Okay. So that's our expectation, and we can write this as in this way, where you know, these are the distribution here is the distribution of transitioning, like the probability of realizing that trajectory, which has to do with, you know, where we start and then the probabilities of transitioning from one state to the other. And you know, again, this maybe is clear, but everywhere we see this is the reward, right? R is the reward. All right, so that's our expected reward. now this, we're trying to optimize this. We're trying to, we're going to perform gradient descent, so we need to take a derivative. So we take the derivative, and things are nice. Theta's inside. We're not integrating with respect to theta. Theta's just somewhere inside of here, and we expect things to be such that we can pass the derivative underneath the integral. You can't do that always, but for most reasonable things you can, and in this case we just expect that we can, because we're going to be bounded, we're going to be integrable, whatever all the criteria are there. But that's not going to be super helpful. Why not? If you remember this from VAE time, these kinds, like these are going to be intractable integrals to perform, right? Even though we've passed the gradient underneath the integral, it's still an intractable integral. Because these are neural networks, and we don't really know. Like this is in general to perform this integral would just be impossible. That's why we call it intractable. For some reason, it's like one of those words where you use, instead of saying impossible, if you can't do the mathematical operation, you call it intractable. Somehow, maybe that's just like less offensive. Like maybe it is possible by somebody else, but for me it's not, so it's intractable. So, okay, great. So we say, what do we do? Well, here comes some trickery. So we go, okay, can't do the integral. We'd like to be able to approximate it somehow, but in this current state, it's not really clear what that would be. So we're going to do the following, and it should not feel obvious that we're going to, like, why this helps. But hopefully after a couple more lines, it will. So we're going to write this gradient in the following way. We're going to, like in generally, this would apply to basically any gradient. But we're going to multiply by 1, right? So numerator and denominator expressed in a special way where it's the probability assigned here from this density function. And then when we've written it in this way, where this is, the denominators here and the numerator, we have the gradient, because that has a particular form. It's the gradient of the log of, the argument here, p. Right? So if you just think about the rules of calculus that you remember. If you take the gradient of log, you get 1 over the exponent, or 1 over the argument times the gradient of the argument up above, right? Yeah.
Can you go through, so for PAE, it was intractable because we did that distribution of data because it's greater than the incarnate space. Why is this intractable here? What's the difference?
I mean, it's for the same thing. Like, it's the same thing. This is some really, really complex. It's a neural network, so some really complex function of the trajectory. Same thing for the reward in some sense. We don't even have a parametric form for it. I mean, we could try to come up with it, but like we don't. Yeah, like we just don't even know. We don't know what we're starting with, really. So we just say, that's what I mean. Like, we don't say it's impossible because maybe somebody comes along and is like, actually, that was so easy. Let me show you. But for right now, we don't know. That isn't clear, so we call it intractable. Okay, so now it's in this form. But so what? How does that help us? Well, here's how it helps us. So now what we do is we write this integral in this way, right? So we just showed that the gradient of p is equal to p times the gradient of log p. Now why is that good? When we put it in here, look what we have. The good news is that we have a p tau d tau. What this means when we have this under integrals, where we're integrating with respect to that that variable there, is that this is the expectation of the rest of the integrand, with respect to this, with this distribution here. So by doing this little trick, we actually got p to show up again out here, in the integrand, and that made this look like the expectation of whatever this is right here, with respect to this distribution. And that's nice because as soon as we have expectations, we know what we can do. Like we're just going to estimate that expectation as the average over some mini batch of trajectories, right? That's what we've done a bunch of times already in the past. It may not be obviously that's what we did, or if you just go back and look, you'll see that we've done this a couple of different times. And it's a really kind of common technique here is that, you know, even when even from the very beginning when we were talking about stochastic gradient descent, what we were doing was estimating the, an average, the expectation, with just a small sample, not the whole data set, but just a small sample, and we just hoped that everything would be fine and dandy, and it turns out that in many cases it's fine. Okay, so that's good. So we now have an expectation, so we can actually sample from this thing, and then compute this right here, and that's our gradient, and now we can compute those gradients, and we can use those in updating our parameters. There is one small problem though, and that is, what on earth does it mean to sample from this probability distribution, which is over the full trajectories, which has a whole bunch of terms in it, right? What does this look like? So this is what it looks like, right? We have our this is the product of a bunch of probabilities, one coming from our policy, which is the likelihood of taking an action given the state that we're in, and then there's the transition probability right here, which is given that state an action, with how does the state get updated? How do we get to the next state, right? So remember how this goes, right? We have a state, we take an action, we get a reward, and the state gets updated. So we get all that from here, and this is a product of all these probabilities, from t equals 0, through the end of time essentially, giving us the whole trajectory. T at 0, t at 1, t at 2, and so forth. That's a problem. That looks pretty bad. Lots of stuff in there. In particular, there's these probabilities that we don't know anything about, at least at this point. But remember that we don't really care about this. We're going to be taking the gradient of something related to this. And what is that thing? Well, it's the gradient of the log of p, of the full trajectory. So what does that look like? Well, we take the log, and of course now we've got, we distribute the log over everything here, and we have all the products turn into sums. So that's what this is looking like now. So that's not bad. And now we're going to be taking the gradient of that, and what's good about that? It's a gradient with respect to the weights, theta. Are constant with respect to the weights, exactly. So when we compute the gradient of log of p with respect to theta, this part right here is constant and goes away, and we just have the gradient of this part over here. So that is really, really nice. And it sort of makes sense given the Markov nature of this process, why the transition probabilities aren't part of the gradient of the log of this distribution. Okay, so that's really good. Now what we have is the gradient of j, this thing that we're trying to optimize, or we're trying to maximize with respect to theta, it looks like this. It is the sum, this series from t equals 0, on into the extended future of our rewards times the gradient of the log of the policy at each, for each of these states t as we move forward. So that actually now is tractable. We have this is just a neural network, so we can compute these values, take logs of them, take gradients of them, meaning we can do the back propagation here, and then just weight them by the reward. So that is our gradient. How do you feel about that? Anybody feel bad about that? Anybody feel just like you've had, you know, like the mathematical equivalent of like a Jedi mind trick, just like pretend, you know, like never. What do they say? Like don't pay attention to the droids, or I don't know. I can't remember. It's like never mind all the weird things that just happened. Like this is going to help. Yeah. All I can tell you is that like we just did a bunch of cool things that got us to the fact. It got us to a point where we could do this integral. Or sorry, we could approximate that integral with this sum. Okay, so the reinforced algorithm then is that the update we're going to make to our weights theta is proportional to these to this this gradient. So what? What does that tell us? Well, what's the intuition here? So one of the really difficult things here about what we're doing is that the rewards are oftentimes, think about like when we were talking about Go. Or just think about any game where like really the object is either to, the object is to win, and you don't know if you've won or lost until the end of the game, right? So the hard part of that is not knowing if you won or lost, but really if you do win, attributing that to the action somehow, right? So like, how should the parameters change? Given the actions that you've taken, or if you lost, again, how do you do that? So think about what this is saying, and this is like the interpretation here. So if the reward is high, think about like if we won. Then what we want to do is we want to change the weights of our policy so that the probabilities associated with the actions that were in that trajectory go up. So it's sort of like a, winner takes all, like, the rising tide kind of lifts all the boats here. They're all, all these actions are going to, we're going to change our parameters in a way that would make it more likely to take that action in the future given that particular state. Right? The reward is high, then we'll be changing the parameters in a way that increases the log of our policy, which is, which will increase the policy, the probability of taking that action. And if it's low, we get the opposite thing, right? Like if this is 0, or just if it's low, then we'll actually figure out it can be negative. We actually be moving in the opposite direction. We won't make any change, but we move in the opposite direction. Or if all the rewards are positive, at least we might if this is still positive, we might move in that direction. But if the reward was much higher, then we would move in that direction in a much more substantial way when the reward is high. Does that make sense? Any questions on that? That's sort of like, we went through all this math, but when we look at this, we kind of get that like the gradients here make sense. All right. Questions? By the way, if you have never seen this before, this would probably feel pretty confusing. And we're only taking 2 lectures on it, right? So if you find yourself interested in reinforcement learning, I'm pretty sure that there is a reinforcement learning, or a couple different reinforcement learning courses taught here in the CS department, and you can spend a whole semester learning about this stuff. We're getting 1 week, so you get like crash course, and then you can decide, should my future include this or not? Decision making under uncertainty, which is a theme of this class, but that's what's going on here. All right. So, couple things to consider here. So one is, it's simplistic to say that the trajectory is good. If the trajectory is good, then all the actions are good, right? This is the reward for the whole trajectory. Remember, like, it's tau in here, not just like, you know, t, like the reward at time t. So this, this is a sum over all those state action pairs, but the reward is the same for all of them. You could think of that as being able to factor that out of the series. So that is pretty simplistic to just say, okay, well, if in the end the reward is good, all the actions that were involved were also good. That's probably not the case. You can think about games you play where maybe you made a lot of really bad moves, like, I don't know, playing chess. This happens to me all the time. I make a bunch of bad moves, and I'm like, oh man, this is bad, but then every once in a while somehow I pull off a win, and you think, okay, well, that happened because maybe they made a mistake, or I don't know, but it really was, I didn't win because of all the actions I made. It was really because of a few of the actions I made, and like, figuring that out can be really a trick. Here, this method skips that all together. It just rewards all actions proportional to the reward over the full trajectory. That probably, I don't know. You may think that shouldn't work, but it does end up working empirically, and we often just say, well, why did that work? Well, all of that misattribution averages out over a lot of examples, right? Like we might actually be changing the weights too far, for an action, in one direction. But if that really is a bad action, it should show up again as part of a trajectory where the reward was low, or you lost, something like that. And so, the fact that you'd see maybe both of those, you could say, oh, that just averages out, and really like the good actions sort of take over. And if you have enough data, that probably is the case, and this will work fine. But let's say we want to do better than that. Remember, these are estimators, and a lot of times when you think about estimators, you think about kind of two things about that estimator. Is it a biased estimator? So like, is its expectation actually different from the expectation of the thing we're trying to estimate? Or is it a high variance estimator, meaning that like, maybe it's not biased, but it has such an enormous amount of variance that like, it doesn't matter. It's like we could kind of get any, in practice we could get kind of anything within that distribution of estimates, and so maybe it's as bad as the bias. So you think about these two things when you think about estimators. So we really have because this attribution is very coarse, it's not really attributing carefully to each of the actions. We have a high variance estimator. How can we fix that? How do we fix that? We need to reduce the variance somehow. What we need to do is we need to replace this reward over the whole trajectory with something else that is that has something to do with the state that we are in at that at each state, at each time t. So what should we replace it with? What are some ideas?
In EAEs, we just estimated the lower bound, I think, everywhere outside of like the center.
Oh yeah.
It's pretty small, so they just started. I don't know if that was watching stuff.
Yeah, that's interesting. That isn't what we're going to do here, but like, yeah, I mean, yeah, there's something cool there to talk about, but I don't have the time to talk about it with you. But if you want to talk about it afterwards, we can talk about it. But we're not going to go in that direction. But you're right. Other ideas, simple ideas. What's the problem with this? It's the reward for the whole trajectory. So what are some simple ideas there?
Randomly pick steps along the way. We're going to take the reward for just those steps.
Okay, so like we could actually replace that with the reward at each step, right? That's a good idea. That could work well in the situation when there's like a reward given at every step, right? Because we would have a value there to use. It would probably work really poorly if we were in a situation where the reward only comes at the end of the game, for instance, because all of these would be, essentially like reward 0. So all those things would just drop out except for like the very last action. So in that case, you'd only be rewarding like the very last action. It's a good idea, but it's not the right one if the rewards are sparse along that trajectory. But it's a great idea if the rewards are dense, like if you're always rewarding it like at every step or every other step or something like that. So thanks for being brave and throwing an idea out there. Did you have an idea?
Well, I was gonna say that seems to only work for, like, would change for different tasks. So it was just a comment.
Okay, because like a similar comment to that. Yeah. Okay. Cool. Other thoughts? Yeah.
Okay, maybe this is crazy, but maybe you could just make it a prediction of whether or not you're going to win, and then it
Okay.
would eventually learn.
Good. That is great. We actually have specified functions for that already in this course. Or yeah, in this course, true. Like this week. What are things that provide you a value that corresponds to the reward given the state that you're in right now, or the state and the action that you take? Yeah, the b value function and the q value function. No, b value, just the value function. The value function and the q value function. That's exactly what those things are doing, right? Those are the cumulative, the expected cumulative discounted rewards given you start in a particular state, that's the value function, or you start in a particular state and you take a particular action, that's the q value function. So we actually already have, at least in theory, functions to give you some notion of that. Good, so that's going to show up, but not quite yet. We're going to do something a little bit simpler. And it's very close to what was suggested earlier, but it looks like the following. First idea. So it looks like kind of a combination here of the two ideas. Remember, what we're trying to reward are actions that lead to good rewards. So this is the reward over the whole trajectory. What if we replace that simply with the rewards that the sum of the rewards that we would obtain starting from time t when we were in this state and we took this action and going forward. This is slightly different. It's not a constant, right? What it's not doing is not including the rewards that we got in the past, right? Like, think about this. Like, if we're in the state and we took this action, we shouldn't accredit, or we shouldn't give any credit to that action for like rewards that came before it, right? That action didn't have anything to do with it. If you think about this kind of causally, we should only ever, reward with stuff that happens after that action, because it's like in its causal cone in some sense. So, so yeah, good. So this is not just the individual reward at that time, because that has a kind of sparse problem. But this is that cumulative reward from that time, from the time that we're at going forward. So that's not bad. That's pretty helpful. Something close to that makes a little bit more sense and makes us look a little bit more like the things we're trying to optimize in the first place is to discount this, going into the future, right? We don't want the rewards that are really, really, really far away from this in the future to also be like accredited to this particular action. Like in general, our intuitions are, the rewards that happen because of the action and then that happen like in the near future after that action are probably you know, because of this, but as soon as, you know, time goes on much longer, you know, we kind of get disconnected, we get decorrelated from where we've been in the past, and so we don't want those rewards to affect how we change the our parameters theta because of that action. So we discount, which is, you know, reducing the reward out in the future. Okay, so these are not bad ideas. They do help. They reduce the variance. Okay, good. So they will help. It will stabilize training. It will give you, it will credit, like it'll give you better parameter values. But there's still a problem here, and the problem is that the raw value of the trajectory isn't necessarily meaningful. You know, like we kind of, I've mentioned this kind of a couple times, and haven't really like focused in on it. But like, you know, if the rewards are all positive, the way that that's formulated, you would still push up on the actions. You know, push up is funny, right? Like you change the parameters so that the likelihood of that action being taken in the future increases, right? And it's you know, it's just simply because of like of the structure of that. But that doesn't seem right? Like if it's low, yeah, it doesn't change as much as if it's high, but you know, you somehow want there to be a way of expressing that so that, you know, if it is low, maybe what we really want to have is to, you know, to change the parameters so that we don't take that action, you know, we reduce the likelihood in the future. So how do we do that? Well, one simple way of doing that is, you know, to take that second idea and now subtract from that some baseline value associated with the state, so that, you know, if these are low, maybe this is something where, you know, this is a bit higher than the low values, and so this would be negative, and that would give you a negative gradient pointing in the other direction. And you know, if this ends up being really high compared to the baseline, then of course it will still, you know, increase the likelihood of that action being taken in the future. So that's great. That's a good idea. The only problem is, all we've done is put a function in there, and we have no idea what that function should be. Any thoughts on that function? We have 10 minutes left. We're almost there. What should that function be? What would be a decent baseline there?
Is that what you use for value function?
Okay, this could be a place where we start to include the value function. What should go there? The value function or the q-value function? Yeah, good. This is just a function of the state. Some sort of, you know, baseline value for that state. The value function is a good idea there. It's only a function of that. And you think about this over here. This looks like a function of both the state that we're in, you know, st, but also the actions that we take going forward. Those would be associated with the rewards that we get. So that looks more like the q-value function, doesn't it? Good. Other thoughts? How to choose the baseline? Simple baseline. Constant moving average of rewards experienced so far from all trajectories. So some kind of moving average. When we say moving, you know what we mean. We mean that like this. Usually, what this means is like it's an average that has some kind of memory, you know, taking into account the past, but usually doesn't take the full past into account. You know, there's like usually some kind of exponential, you know, discounting factor on that to, or something similar to sort of forget the long ago past and just average the stuff nearby. So, you know, if we've, you know, in our mini batch we've seen a bunch of trajectories of rewards, then, you know, something like the average of those, you know, especially like over time or over like the episodes, would give us something like the average reward. And if this is lower than an average reward, then that's like somehow bad because it's, you know, it's worse than average. And if it's higher, then it's good. It's better than average. So that's a simple baseline, easy to kind of implement in code, right? Just kind of keep track of those rewards and however you compute the moving average, include that. So that's a common way to do this. And when we do, and when we're finally to here, and we use that baseline, and this way of computing like the constant in front of the this gradient here, this is the plain vanilla reinforce algorithm. Okay, that's like when you see reinforce, you're reading a paper to say we train this by reinforce. That's what they're doing. These are the gradient estimates that it's using. Okay, can we do better? We already mentioned this. Jacob had pointed this out. Somebody else pointed it out earlier. Can't remember who, but we can be using the Q value and the value function here. And in fact, this right here is a really interesting value. The Q value of a state in action minus the value of the state. And why is that interesting? Well, what happens if this is positive? What does that say about the action?
The action will on average give you a better value than the state.
Yep. I mean, and it's funny, right? Because it's just this one action, and it's this expectation over the rest of the trajectory. But on average, the trajectories that come from taking that action in this state are giving you higher rewards than on average. This is the average over all the actions, including the action that you take in that state. Good, and if it's negative, it's worse, right? So that's actually really that's really interesting. We didn't notice that when we first introduced it, but it's exactly the kind of thing that we want to be able to say how good a particular action was in this state. So if we now replace, where were we? We now replace this coefficient here for weighting the gradient of the policy with respect to that, having taken that action. If we now use the Q value and the value functions, we get a really excellent estimator here of our gradient of our function j, our objective. And this is what is actually known as the actor-critic algorithm. So it's reinforce, but where that coefficient in the series is given by this difference of the Q value and the value function at that state in action. And this is actually a function that gets another name called the advantage function, right? So this is telling, the value here is telling you the advantage that you got from taking that particular action in that particular state. If it's positive, there was a positive advantage. If it's negative, it was a negative advantage or a disadvantage. So it's called the advantage function. And it's called actor-critic. Why? Well, you have an actor, the policy. It's the thing that's making decisions about which action to take in the particular state. And then you have your Q value function, which is the critic. It's telling you like how good or bad that action was. It's assigning a value. So when these things work together, we don't call it policy gradients. We call it actor-critic algorithm. What's the problem here, though? Why did we even go to policy gradients in the first place? Because Q was hard to learn. So this doesn't get away from that at all. Like it's still the case. So you may not be able to implement an actor-critic algorithm if you're still in a situation where your Q is difficult to learn. Again, very complex state and action spaces. But if not, you could have just done deep Q learning itself, but you might try this because of various reasons. Like remember what's happening here, which is really nice. In the policy gradient, so in deep Q learning, we got an implicit representation of the optimal policy through the optimal Q value function. With policy gradients, you're actually getting an explicit representation, a neural network of the policy, and perhaps that's what you want. In which case, you know, policy gradients is a great way to go, and you know, even if you still can compute these, this might be, and if you can, you know, you might get the best of both worlds where you can have your explicit policy, given by neural network, but it's trained in such a way that the way that you attribute the value of actions is done in a very like principled way. Make sense? So policy gradients, active critics in particular, kind of when you combine the deep Q learning with the policy gradient learning. And time's almost up, but this is what, you know, this is pseudocode for what that looks like. I would really like this. Like, we go through like tons of slides, and it feels really complicated, and they write down the pseudocode for how to train, and you're like, 10 lines, no big deal. Got this. Got this. No big deal at all. I just, you know, it's this thing right here, this advantage value, like this coefficient. This is like, that makes all the difference. And that's what we spent most of our time talking about today, is like how you might get those. Okay, really quickly, when time is up, I'll just say, here's a really interesting example that combines a bunch of the things that we've learned in this, in this course so far. Using reinforce to train a model that will classify something like an MNIST object, you know, one of like a handwritten digit, but it only gets to glimpse a small part of the image. And what the model is learning to do is to take multiple glimpses. So, you know, think about it like in this way: take some sort of random glimpse, like this right here, and it kind of, you know, it sees this arrangement of pixels, and you say, okay, where should I look next in the image, given that I've seen this already, so that I maximize my ability to classify the object, the digit in this image. And you know, I'm going to limit myself to like, I don't know, 5 glimpses, 10 glimpses, whatever. This is motivated a bit by the way that, I don't know if anybody's ever studied, you know, like in neuroscience, think about like visual system, you think about like how eyes like obtain information. You'll know that you actually don't ever really like stare at anything unless like you kind of are either like dazed, in which case you're not really staring, or you really concentrate on staring. But otherwise, your eyes are continually kind of like moving around the view that you have, like taking in relevant information and trying to aggregate that into some kind of representation of like the environment that you're in. So it's kind of motivated by that. So how would we do this? Well, we're going to formulate this as a reinforcement learning problem. Our state is going to be the glimpses we've taken so far. The action is going to be basically choosing coordinates within the image of where to like center the glimpse next. And then the reward is going to be at the very end, if we classify, we're going to get a 1 if we classify the image correctly, and a 0 otherwise. Okay. So we have convolutional network ideas here because we have an image. We also have a sequential idea here, so we're going to need something like a recurrent neural network, and then we're doing this all within the learning paradigm of reinforcement learning. And the way this works is that we have our convolutional neural network that's going to take in, you know, the patch that we're looking at, represent it somehow so that it can give us the prediction. You know, it's going to like essentially predict. You know, it's like a regression of where to glimpse next. We're going to represent that. We're going to accumulate that state for that sequential behavior in an RNN. So the output of that will now be input to the next. We'll have hidden states that will be updated along the way. Maybe we take 5 glimpses, and then the output from that final node there, we will send to a softmax, and we will classify. We'll try to, you know, say we'll be computing scores, and we want the highest score to be associated with the correct class of the image. And instead of this being supervised now by like cross entropy loss, as we would typically do with a classifier, this is now going to be learned via reinforcement learning. So we're going to get rewarded or not using our reinforced algorithm. And this is called a recurrent attention model. I wouldn't say that you see a lot of these, but it's kind of a cool combination of these things, and it can help you study things like the visual system. Anyways, where do you see policy gradients otherwise? AlphaGo, so the model that learned to beat the world champion at Go is at its core a policy gradient method. It also has built into there like interesting ways of using Markov tree search ideas. I mean, so like it actually builds in a lot of understanding of the game. So they iterated on this. They went to AlphaGo 0, which was like AlphaGo, but didn't require any human play. It played against itself. That's kind of cool. That's like the 0 part of this. And then there was Alpha 0 next, which was it learned how to play not just Go, but a bunch of other related types of games like chess and so on. And then they went on to do other things like Mu0, which got rid of like knowing anything about the rules at all, but it has a method for like learning the rules of the game while playing the game against itself. So they kind of kept iterating and like making this more and more abstract. But at the core, it's policy gradients. You can have a lot of fun with like playing around with these ideas. At OpenAI, they have something called the Gym. This is this is like an SDK, like a Python SDK that you can download and play with, and it has all these environments in which you can do reinforcement learning, and it's a pretty cool way to get started and have a lot of fun. And that's it. So policy gradients, Q learning, policy gradients challenge can be sample efficiency, the attribution problem. Q learning, the problem there can be the complexity, the ability to explore the space, and guarantees policy gradients do converge to a local maximum. That's often good enough. Q learning, 0 guarantees that you have the optimal, like if you can get your loss to 0 or very close to it, you have the optimal Q value function because it will satisfy the Bellman equation. And that's that. Cool. All right. Thank you very much. This is the last lecture because we're canceled for next week. I'll stick around for questions or whatever, but good luck with the final projects, and reach out to me on email if you have questions. TAs will still be holding their hours so they can answer questions as well. And thanks for a great semester. So I'll see you sometime, hopefully in the future, when you're doing great things with ML. Responsible, moral things with ML as well.